Hi everyone. Today we're starting Chapter 4, Congruence in Triangles. You should already have your unit objective sheet with all the information on it for Chapter 4. So right now you just need to have your notes out and ready, and we're going to take a look at Section 4.1 today. If you do need to pause the video at any time, feel free to stop it so that you can take notes properly. Okay, the three big ideas are on your unit objective sheet, so read through these. I'm just going to skip over them now. Section 4.1, we're going to talk about applying the triangle sum properties, and our focus is on how we classify triangles. All right, so first, definition of a triangle is a polygon with three sides. In the triangle I have pictured below, we can name it by its vertices. So we can call this triangle ABC, or we can also use the symbol for triangle in front of the letters ABC. Now, the order of the letters doesn't matter. You just have to make sure you have all three and they go in corresponding or consecutive order around the triangle. So another potential name for this triangle is triangle BCA. Okay, or we could have called it triangle ACB. The point is just to have a proper name for it so that we can identify it in a diagram. All right, so I would like you to pause the video here and copy down the slides. Okay, so at this point we have three names for triangles classified by their sides. These most likely are familiar to you, but just to go through them quickly, a scalene triangle has no congruent sides, meaning every side is a different length. An isosceles triangle has at least two congruent sides. Okay, so that could mean that we have more, but at least two. Most of the time there will just be two. And finally, an equilateral triangle has to have all three sides congruent, as we see marked. Second way we can classify triangles is by angles. So an acute triangle has three acute angles. A right triangle has one right angle. The other two angles have to be acute. An obtuse triangle has one obtuse angle. In the diagram we can see that angle is right here. And then an equiangular triangle goes right towards its name, equal angles, so all three angles are the same degree measure. And in this case, we're going to talk about in a second degree measures in triangles, but all three angle measures are going to be 60 degrees. Okay, so what we're going to do is talk about how to classify a triangle when it's in the coordinate plane. So triangle PQO is drawn on our coordinate plane where O is at the origin, P and Q have their coordinates. So we need to figure out if this triangle is a right triangle. Okay, so first, as far as classifying goes, I'm going to show you our hint. We need to use the distance formula. So I need to figure out what the lengths of some of these sides are. Now when I look at the triangle, I can clearly see that the side from P to O is going to be a different length from the other two. So I know that this triangle is either isosceles or scalene. So I'm going to check the distance from P to Q and the distance from Q to O to determine if they're the same length or different lengths. So first, for P to Q, using the distance formula, I'm going to subtract the two x values. So -1 minus 6, and that's going to be squared. And then I'm going to subtract the two y values, 2 minus 3, and then square it. Then we add them and take the square root. Okay, so here I get -7 squared plus -1 squared. That gives me values of 49 and 1, which is the square root of 50. So I'm going to leave that as the square root of 50 because I don't need to know the exact decimal value of this length because I can still compare them as a radical. I'll show you what I mean. Let's take a look at Q to O, that distance. So the square root, and we set up our distance formula, and we're going to plug in our x values first, 6 minus 0, and then our y's, 3 minus 0. So I get values of 6 squared and 3 squared, which is 36 plus 9. So I'm getting the square root of 45. So even though I don't know the exact length in terms of a decimal, I can clearly see from this information here that PQ's length is not the same as the length of QO. Okay, so Based on my information, I can now come up with a classification of a scalene triangle. Okay? Now I need to figure out if this is a right triangle. So I'm going to be looking at the angles for this one. But more specifically, as we see in the hint, I need to use the slope formula because in order to determine a right angle, I need to know if those lines are perpendicular. Now, the only spot where I'm really concerned or where I think there might be a right angle is when PO meets QO. They're at the origin. Okay, so I need to find the slope of PO and the slope of QO. So we're going to come down here. So the slope of PO, I'm going to use the change in y over the change in x. All right, if I go back up to look at my points, I'm going to use 2 minus 0 over negative 1 minus 0. That gives me values of 2 over negative 1. So the slope of line PO is negative 2. Okay, next I need the slope from Q to O. Still using the change in y over the change in x. So if I look at my values again, I have 3 minus 0 over 6 minus 0. So come back down here. 3 minus 0 over 6 minus 0 equals 3/6 or a half. So to figure out if these form a right angle, I want to see if those two segments are perpendicular. And I know that when two segments are perpendicular, their slopes will multiply to equal negative 1. So if I plug in the slope of PO, negative 2, and I multiply that by the slope of QO, 1/2, I do get negative 1, which confirms that I have perpendicular lines. Once I see that those lines are perpendicular, my conclusion is that this is a right triangle. So coming back up to the question now, how would I classify triangle PQO? It would be classified as a scalene right triangle. Okay, let's move on. Next thing I want to talk about are angles that show up in a triangle. Okay, so we have two sets of angles here. We have the interior angles. Okay, I have those marked in red right now, the three angles on the interior of the triangle. Now, what we also have are these angles called exterior angles. Exterior angles are when we extend the sides of the triangle. So, for example, I'm going to highlight this so you can see what I'm talking about. If I extend this side of the triangle past the vertex, okay, what I've done is I've created a linear pair of angles. And the one marked in blue is an exterior angle because it's not inside of the triangle's boundaries. All right, so I have three exterior angles. Each one matches up with one of the interior angles. So the exterior and interior angle pairs are linear pairs. And that's important to remember because we know that they're going to have a sum of 180 degrees. Okay. One other thing I wanted to note here was that there are actually two sets of exterior angles because if we extend the sides in the other direction, we would create a second set. We only want to work with one set at a time. So when you're drawing your exterior angles, you want to go in the same circular direction. So for example, I'm going counterclockwise when I draw these. So my first one is drawn this way. My second one starts and goes off to the left. And then my last one, again, continues off to the right so that I'm always going in the same direction, in this case, counterclockwise. Okay, so we have two theorems in section 4.1. The triangle sum theorem should be very familiar. The sum of those three interior angles is 180. Just make sure you copy this into your notes, but we're not going to go over it since this is something you've seen before. The second theorem is a little new. It's called the exterior angle theorem. So for this one, what it's telling us is if we take the two angle measures, A and B, Okay, they might not be congruent, so I'm just showing you where they are with the arcs right now. They can be different numbers. If I add those two together, I'm going to equal the value of angle 1. Okay, that's shown down here in this equation. The measure of angle 1 is going to equal the measure of angle A plus the measure of angle B. So I just want to show you a quick example as to why this happens. So let's say the measure of angle 1, we'll start with that one. Let's say that that's about 120 degrees. Okay, I'm going to mark one more angle in my diagram to work with here. I'm going to call this interior angle angle 2. So if angle 1 is 120, I know that angle 2 is going to be 60 degrees because those form a linear pair. All right, so back to my triangle sum theorem from above. All three angles in the triangle have to add up to 180. So if that's true, then what I'm going to do is say, okay, my measure of angle A plus my measure of angle B plus my angle 2 would be 180 degrees. All right, well, I already know angle 2 is 60, so I'm going to substitute that in. Now what I can see here is that if I subtract 60 degrees from both sides, I get the measure of angle A plus the measure of angle B equals 120. If I look back, that's the same thing I had for angle 1. Okay, so it's based off of the fact that these sums are 180. 1 and 2 add up to 180, and A, B, and 2 add up to 180. So transitive properties telling us that angle 1 and the sum of A and B must be the same. All right. So we're going to use that in a quick example right here. Go ahead and pause the video and try this one on your own. Okay, so let's see how you did and if you got this one right. Since we have an exterior angle, 2x minus 5, and two interior angles that are not adjacent, x and 70, we can use the exterior angle theorem to set up an equation. 2x minus 5 has to equal the sum of x and 70. So to solve for x, I'm just going to solve the equation by isolating the x variable. So the first thing I'm going to do is add 5. I have 2x equals x plus 75. And now I'm going to subtract x from both sides and get x equals 75. So I'm going to plug those back in to make sure this value is working. So x is 75 degrees. Okay, if I plug it in for the 2x minus 5, 2 times 75 is 150 minus 5 equals 145. So let's find our last missing angle, JKL, to confirm that it's going to work for both of these values. So inside the triangle, 70 plus 75 plus angle JKL has to be 180. So 70 and 75 is 145. Oops, sorry, that's JKL. Which means that angle JKL would have to have a measurement of 35 degrees. All right. And if I look at JKL and my 2x minus 5 angle, 35 plus 145 is 180 degrees, which is a linear pair. So I've confirmed that my x value must be 75. Okay, this is just a vocabulary term I'm going to have you write down. You do not need to write this proof down. I'll explain this to you later. But sometimes when we're proving certain theorems, we might need to add a line, array, or a segment into a given diagram. Whenever you add a line that wasn't there to begin with, this is called an auxiliary line. But this is a viable way to go through a proof. If you think you need it, draw it there. Okay, again, I'm going to go over this later. So just make sure you have the definition copied down. Okay, last in 4.1, we have corollary. Corollary to a theorem just means that from the original theorem, this is something else we know is easily proven true. Okay, so definition is a statement that can be proved easily from the theorem. The corollary below follows from our triangle sum theorem. So this says that if, the acute angles of a right triangle are complementary. So if we look at our triangle, we know that these add up to 180. So if angle C is a right angle, then the measure of angle C plus the measure of angle A and B has to equal 180. Well, if C is 90, then we can use our subtraction property to show that the measure of angle A plus the measure of angle B has to equal 90 degrees. Okay. All right, so this last example, I'm going to skip for now, okay, but you can try this one on your own. So if you want to pause the video here and give it a try, we're just going to come up with what the other angle measures are based on the information. Okay, but this is going to be the end of the video for section 4.1. So the rest of this today during class, we'll practice and see if we understand all of these theorems and triangle classifications.